So, we were discussing the response spectrum analysis. Actually, let me give you a quick overview of what we are currently discussing. Just a quick recap. We are discussing the code based seismic analysis procedures, which are conventionally used for structural design purpose or structural evaluation purpose, but they are recommended by building codes, which means primarily they are based on the use of linear elastic computer model with some implicit considerations to consider nonlinear effects, right. And there are three of such methods. One is ELF, and then is RSA, and third is the time history analysis. All three of them are based on the use of linear elastic model, right. So, there are some common concepts, seismic design concepts, which are associated or common to all three methods. For example, the concept of R, response modification factor, the concept of CD, the concept of risk category, the concept of importance factor or overstrength factor. They are all common to these three methods, right. Only the calculation procedure to determine that EH, right, or EV, that calculation procedure is different for these three methods, which will go ultimately in your load combination and result in the determination of seismic design demands, right. ELF procedure is the basic one. It is based on the idea that you can calculate some static forces which can be applied to your computer model, which can represent the future loading of earthquake, and then you can combine that effect with the gravity load and other loads to calculate the seismic design demands. RSA is conceptually more superior. It is based on the idea that we should not only apply one fixed load pattern in a kind of triangular pattern distribution to calculate seismic demands. Instead, we should consider the patterns associated with each of the vibration modes of the building. We should apply a pattern which is proportional to the vibration mode shape of the building, and it should not be one pattern only. It should be 3, 4, 5 or as much number of modes which you want to consider in your analysis. Those much number of patterns should be applied separately, and then the responses should be combined approximately using a statistical combination rule, for example SRSS. So, you have to calculate the equivalent static forces for each mode separately and apply them in a static manner. So, in order to calculate those equivalent static forces, we need to understand the dynamics of that building itself, because unlike the ELF, where the formula to calculate equivalent static forces is primarily governed by the hazard level only, with very minimum input from the structure side, right. Here the structure will play a main role in the calculation of equivalent static forces patterns, right. The structure's mode shape and time periods and the structure's damping will play a main role, right. So, without actually going into detailed mathematical formulation, I directly told you or explained to you the formula to calculate equivalent static forces for each particular mode. All you need to know is the modal participation factor of that mode and mass matrix, which is already available, and the spectral acceleration from the spectrum corresponding to the time period of that mode, and then the mode shape vector for that mode. These four information is required to calculate the equivalent static force pattern for that mode. So, we were discussing its main steps. First was to perform the eigenvalue analysis. Obviously, there should be a step 0 which should say that you should construct a computer model first with M and K matrices, and then you should perform the eigenvalue analysis to calculate the modal properties. Then you should estimate the modal damping ratios for each mode, what xi should be used. Generally, it is 5% for all modes. Third step was to construct the response spectrum to be used for this analysis. For the design of new buildings, obviously you have two options, either use the code based spectrum or go for site specific analysis. And for analysis against some past earthquake, you can construct its response spectrum, and in that case obviously you will be having the history of that earthquake already with you. So you will be running the single degree of freedom system again and again by varying its time period to finally plot its response spectrum, acceleration response spectrum. So once these three steps are completed, we can proceed to the determination of seismic response for each mode separately, right. That is step 4 actually. So I gave you one example. In this particular building, if I just consider x direction, we can, and let's assume that only 3 modes are participating in its dynamic response. So I have extracted the phi 1, phi 2, phi 3 for this 8-story building, and then I calculated the modal participation factors for these 3 modes, gamma 1, 2, 3. Then I constructed the response spectrum which I want to use for the analysis of this building, and this is the equation which is prescribed by ASCE 7-16. It has a linear ascending part, then a peak plateau, and then declining part again have 2 parts. One is having this equation, other is this equation. So these are the codal provisions to determine the design response spectrum using ASCE 7-16 or IBC 2021. And then there are provisions about site specific analysis. If you lie in that category, you should go for site specific analysis, but there are some exceptions also, that if you lie in any of these categories but you still lie in the exception, again you are allowed to use code expression. So this is another example where I use 2 different codes to plot the response spectrum of the same site. So the black line corresponds to BCP 2007, orange line corresponds to BCP 2021. So I kept the occupancy category and risk category comparable so that I can plot them on the same graph. So now let's go to step 4, which is the computation of response for any nth vibration mode, right. And obviously this step 4 should be repeated for second mode, third mode, fourth mode, so for any number of modes you want, right. So I will explain how code guides us about how many number of modes should be used in this analysis, but first you should know that the dynamic response is mostly contributed by only first few modes. So no need to go, for example, more than 10th mode, for example, in a particular direction, if you are talking about a regular building. But there can be cases where the building geometry is such that first 20 modes are participating to make some reasonable modal mass, cumulative modal mass. So in that case you can go beyond that. So the first step in this step 4 sub step is to pick the peak displacement and peak acceleration from the corresponding response spectrum corresponding to the time period of that mode and the damping ratio of that mode. The code equation is by default for 5% damping, right. So let's say that you plotted that code expression, spectral acceleration versus time period, and it is by default the equation is for xi equal to 5%. Then you can, if you want to plot it for some other damping, let's say that you assume some other damping, then there are empirical equations to modify this spectrum, obviously empirical factors. So you put your damping in those equations, they will give you a factor to modify this spectrum, and there are a lot of such equations available. Obviously if you want to plot this spectrum for 10% damping, the factor will be less than 1. So you will be reducing that spectrum to to a lower level, right. If you want to plot it for 2%, factor will be greater than 1. So there are several equations which provide you such modification factor. They are called damping modification factors to modify the spectrum height based on the damping, right. There are some building codes which directly provide the equation in their main provision, which is the function of damping ratio as well, so that you can directly plot the curve according to your own damping ratio. I think if I am not wrong, then up till ASC 7-05, the equation for spectrum was the function of damping ratio also, right. So for 5% it reduced to the same, almost same equation, but for any other damping there was a modification and then you plot for that damping. So let's say that and obviously once you have the spectral acceleration response spectrum, you can convert it into spectral displacement also, because you know that spectral acceleration is omega square times spectral displacement, right. So SA and SD are convertible if you have the omega known, right. So point by point you know the omega or time period, they are interconvertible. So point by point you can convert SA versus time period into SD versus time period, right. So code in a sense also provide you the displacement response spectrum. So if you convert SA into SD, you may have a line like this, right. It will be increasing with time period. So the first sub step is that for your natural time period, let's say you are doing it for n equal to 1, which means first mode. So corresponding to first mode, pick your SA value and pick your SD value also, right. This is first sub step. Second is compute the floor displacement and the story drifts. Drift is the relative displacement between two stories at any jth floor from the following equation. Now dn is coming from your response spectrum, displacement response spectrum. It is SD, right. So I used SASD, but this text is using DNAN. So let me just write, this is SD for any nth mode and this is SA for any nth mode. So for any story level, I can calculate the story displacement from this expression. So simply mode shape ordinate at the jth level for that particular nth mode will be multiplied by gamma n, will be multiplied by the spectral displacement. So both of these two numbers which I encircle now, gamma n and dn, they are constant quantities for any nth mode, right. So this is a constant number. This number is being multiplied by the phi vector along the height. This will give you the story displacement for that mode, right. So the story displacement in RSA can be directly obtained once you know the spectral displacement of that mode, right. So the basic idea of mathematical formulation is also this one, that in RSA you first calculate the story displacement and those displacements can be multiplied by the K matrix of the structure to calculate hypothetical equivalent static forces. So that expression which I showed you, this one to calculate the story forces is nothing but story displacements multiplied by the K matrix, right. So you please check its mathematical derivation, right. So the first step is we calculate floor displacements using the spectral displacement from spectrum, right. So it's simply distributing one displacement coming from spectrum along the whole height of the building using the pattern of mode shape, right. So for any jth mode you can calculate uj n, which means if j is, let's say, fourth floor, so ujn is what, the displacement of fourth floor because of first mode only, right. And similarly, if we want to calculate drifts, it will be simply upper floor displacement minus lower floor displacement. So, these two quantities which I am encircling now, they are not dependent on floor number. So, simply the mode shape number will be different for each floor. So, simply we will have this difference in the bracket and again gamma n and dn. So, then third step is to determine the equivalent static forces, and for that you need to first calculate a load pattern which is denoted here as an Sn, and it should be multiplied with the spectral acceleration of that mode. So, Sn is basically this whole thing, this whole constant pattern is Sn, and this pattern is being multiplied by the spectral acceleration of that mode, right. Last step is to compute the Storey forces, everything, Storey displacement, Storey shear, all those Storey displacements are already available, right. But if you apply these equivalent static forces and compute the Storey displacements as a response, you will get the same Ujn, because the Storey forces are calculated simply by multiplying those displacements with K matrix of the structure, right. So, you apply those Fjn or force at each Storey for any nth mode and compute all the responses, whether they are Storey level or they are local element level. So, any element force, bending moment, shear force, everything can be calculated by performing the static analysis of your structure against this Fn vector, right. So, this is for nth mode only, any particular mode. So, you solve F is equal to Ku, and F is actually what? Your Fn, right. So, U will be, or all the responses will be for that mode only, right. Repeat that process for n equal to 2, n equal to 3, compute the separate responses for second mode, separate responses for third mode, and then SRS them, right, combine them using square root of the sum of squares. So, all the responses coming from, let us say, 5 separate analysis, their numbers are actually combined using SRSS. So, one major limitation of this SRSS is that if the response quantity from first mode is in negative direction, response quantity in the second mode is in positive direction, SRSS will make all of them as positive, right. So, if for example, moment in a particular beam is minus 50 from first mode, plus 30 from second mode, right, and let us say plus 10 from third mode, and let us say there are only 3 modes to be considered, then SRSS will neglect this minus sign, because when you scare it, it will become positive, right. So, negative responses will simply become positive, and finally, the SRSS will give you you can say a positive answer always. So, RSA can never give you a negative answer if you are using SRSS, right, and that positive answer is the conservative estimate of the maximum response which your structure can have, right. So, this is one of the major points of criticism on this RSA procedure, that it does not account for the cancellation of responses from different modes. For example, true dynamic analysis RHA or THA, it can handle that direction effect also, right. So, although it is not based on the mode shapes idea, but since it is calculating the response for each time step, so if there is at one particular time step, if it is positive and then it goes to negative, it accounts for that reversibility or change in direction of the response. RSA does not account for the change in direction of response, right. So, even if you in load combination you apply RSA as plus RSA and then minus RSA, even then the minus answer will be the most conservative number, and you will not be able to account truly that effect which can be handled or accounted using dynamic analysis only, right. So, this is one of the major uncertainties in RSA, the modal combination rule. So, there are some other more you can say sophisticated modal combination rules are also devised, but SRSS is mostly used for its simplicity, but it is approximate also. It will be equivalent to assume that the peak response for each mode occurred at the same time step, which is not the case actually, right. So, modal RHA is a method, if you remember that mode superposition method, that has the capability to give you the fluctuating response for each mode, right. If you remember the structural dynamics classes, we were able to calculate the dynamic response of the structure, and in that we were having a term for first mode plus a term for second mode and plus a term for third mode. So, we were able to actually get the fluctuating response for each mode separately, which we were combining to get the total response. And if you actually perform some example using that method, you will come to know that generally the peak response for first mode will occur at a different time step, peak response for second mode will occur at a different, and third will occur at a different time step. So, if you are directly adding the peak responses, it will be unrealistic, right. When first mode is showing you the peak displacement, second mode response may not be showing you peak. So, directly adding them may not be a correct you can say accurate assumption. So, whenever you have peaks from different cases and you want to combine them, there are different statistical methods which give you some resultant peak, and one of that method is SRSS, right, that you do not add the peaks directly, you scale them, sum them and take its square root. So, you normalize them, kind of get as a resultant you can say combined response, right. So, here in this slide I show you one example of the equivalent static forces for a 5-story building. It is a 2-dimensional shear building with a constant mass, right. So, these are the forces calculated for first mode. It is actually the pattern, it is not yet multiplied with the spectral acceleration. So, it is actually this thing gamma n multiplied by story mass multiplied by phi j n. Each of the force is calculated using this expression, right. So, it is actually S1 is gamma 1 times the mass matrix multiplied by the phi 1, right, phi 1 vector. So, individual force obviously will be written as a scalar quantity. Fjn is the force at any jth floor, but if you want to write the whole vector, whole pattern, it is the F bold n. So, Sn is showing you the pattern, it is this thing, and An is the spectral acceleration for that mode, which you pick from the response spectrum. This is for second mode pattern, third mode, fourth mode, fifth mode. If the story masses are constant, the force patterns will resemble the mode shape pattern, right. So, you can see here that this is all forces in one direction, but the second mode pattern is showing you some forces towards left hand side, some forces toward right hand side. So, this pattern is going to deform your building in this shape, right. Similarly, this pattern is going to deform your building in this first mode shape. This pattern is going to deform your building in this third mode shape, right, and fourth and fifth. So, you can calculate as much as force patterns, equivalent lateral forces, as much as number of modes you want to include. This was a 5-story 2D building, so it had 5 modes only. So, we can have at maximum 5 force patterns. and we apply them one by one, calculate any response quantity, let us say R and O, where N is the mode number and O denotes the maximum quantity. Let us say axial force in a column can be denoted as R and O for any nth mode. So, we calculate that same axial force in the same column for first mode, then for second mode, then for third mode, and then we SRSS them. So, this is SRSS, right, that we for any n 1 to capital N, where capital N is the number of modes we want to include in the analysis. So, this will approximately give you the combined peak response, any response R, right. So, please focus on this symbol, it is not equal, right. In the modal RHA, since we have the time history for each response for the whole duration, so we can directly stitch them. At each time instant we exactly know that this is peak, but this is not peak. So, we can directly stitch them to get the combined peak response, but here we only have peaks for each mode, we do not have the complete histories for each mode. So, therefore, we approximately combine them to get the peak response, right, and again that approximate response will always be positive, right. There is a more sophisticated modal combination rule, CQC method, complete quadratic combination rule, and this combination rule is recommended for cases where the natural frequencies are not well separated, right. So, for regular kind of structures where natural frequencies are well separated, we can use SRSS, but for special cases we should go for CQC method. And in CQC method, the basic idea is that when you are combining modes, the effect of one mode on the other, or the correlation between two modes, should also be considered while combining them. In SRSS, what we are doing, we are considering each response, each R and O is considered independent of the other, right. So, there is no correlation between different modes which is being accounted here, but the expression for CQC method, if you see, like RIO is the same R naught response coming from ith mode, and RNO is the response coming from nth mode. So, you will be considering two modes at a time and a correlation factor between two modes, right, a correlation factor between two modes, which is called which is shown here as rho IN. It varies between 0 and 1, and if the I equal to n, the rho will be exactly equal to 1, and in that case this will reduce to SRSS, right. So, I will not go into detail of how you should compute this rho IN, but the basic idea I explained, that here you do not consider two different modes independent, you somehow account for their correlation also, right. Because really if you look at the real case, if a building is vibrating in a particular vibration mode, it may have contributions from the other modes as well. So, maybe the assumption that each mode can be completely seen independent of the other may not be true in certain cases, and in those cases you may go for CQC rule. So, in this 5-story building, obviously capital N will be 5. For your real 3-dimensional structure, it can be 100 or 200 also. Theoretically there can be thousands of degrees of freedom, but you should always consider that only lower modes contribute the most. So, start with maybe first few modes, check whether they fulfill the requirement of building code for the minimum number of modes to be considered. If they fulfill, then you should go with that analysis. So, the modal combination rule will truncate. If you want to consider only 10 modes, but your actual capital N is 3000, you will truncate that SRSS at just 10 modes. You will not add 11th, 12th, 13th response, right. only response from first 10 modes.